Let's review projectile motion. How about? So, what we've got here is a sort of classic looking projectile motion situation where we have initial velocity v, um, an object fired at an initial velocity of v at angle theta. Now we can take that velocity and we can break it up into the horizontal vx and vertical vy portions, and together those are vectors which add together to form the initial velocity v at angle theta. So one thing that we can say right off the bat here is that since this is a right triangle here, these vectors form a right triangle. One thing we can say is that v squared, right, the hypotenuse, is equal to vx squared plus vy squared. So that's always going to be true for this because those vx and vy are perpendicular components, right? This makes a little right triangle here. I can draw the little right angle ideal there. And so we know that this Pythagorean theorem is always going to be true here. Okay, we can use a little trigonometry here, and we can say that, well, for Vx, right, the horizontal component, if we look at our little right triangle here, Vx is equal to V times the cosine of theta. Okay, and also for Vy, we can say that Vy is equal to V times the sine of theta. Okay, so again, the idea here is we can take that initial velocity V, because usually the way these problems are set up, you fire, a cannonball or whatever it might be, an arrow, you fire at it at a certain velocity at a certain angle. Well, that velocity is, it's helpful to break that up into horizontal and vertical components because they will act sort of independently. And what I mean by that is, if I go back to the red color here, and let's talk about the horizontal. Horizontal, of course, is x. So the x position anywhere along this path, okay, is going to be equal to the initial x position, wherever we start. Now, usually that's going to be 0, but go ahead and throw it in there just to make the equation complete, plus the velocity in the x direction. This is why we have to break them up into, x and y, vertical and horizontal, times the time that it travels in that direction. The horizontal, remember, is not under the influence of gravity. So the horizontal velocity does not change throughout the entire trip, throughout that entire time t. Okay? The vertical, on the other hand, is a little more complicated. So y, the position y at any given point during this trip, is equal to the initial y position. Again, usually this is going to be 0, but not always. Plus the y velocity, the velocity in the y direction, times the amount of time that it travels there. So far it looks just like the x. However, the vertical, the y, is under the influence of gravity. So we have to add in the influence of that acceleration due to gravity, which of course is g and t squared. Okay, now what couple of things that sort of tie these problems together. One thing that ties these problems together is what we already talked about over here with the velocities, that initial velocity is broken up into vertical and horizontal components. And the second thing is that this t right here in the horizontal equation is exactly the same as this t right here. In other words, the same amount of time that it takes this object to travel this distance, x, is the same amount of time it takes for that object to go all the way up to the highest point up here and then all the way back down to the lowest point back here. So those times are exactly the same, which makes sense when you consider it starts and stops in the same spot or together, right? So anyway, let's look at a sort of a sample problem here. So let me just kind of make up a situation here. So let's say, I'll go back to the black pen here, and let's say that we have an initial velocity of 20 meters per second. And we have, that is fired at an angle of, let's say, 60 degrees. Okay, so what does that mean for us? Well, let's start breaking this apart here. So let's say we have Vx is equal to V, which is 20, times the cosine of 60 degrees. And that means that the horizontal component of the velocity is going to be equal to 10. I was going to say, I thought it was 10. Remember my trigonometry here, cosine of 60 is 1/2, right? So that means the horizontal velocity is 10 meters per second. Okay. The vertical velocity, Vy here, is going to be 20 meters per second times the sine of 60. And 20 times sine 60, that is equal to 17.3 meters per second. Okay? So now, here's where it gets maybe a little bit tricky, because now if what we're trying to find out is what is the range. Range basically just means x, right? So range means, how far does it travel? Okay? So, or the target distance, or whatever you want to call it. It's the horizontal distance. How far is it going to travel? Well, as we've already talked about, that depends on t. Well, t depends on gravity and initial velocity. So we're going to use this equation right here to figure out t, and then we're going to use this equation right here with that t to figure out how far this thing travels horizontally. All right, I'm going to kind of scoot up here a little bit so I can fit this in here. So, all right, let's talk about this one here a little bit. This is the equation we're using. Let me clean that up a little bit. Okay, so this is the equation we're using. The y position is equal to the initial y position plus the y velocity times the time plus 1/2 gt squared. All right, so let's fill in some stuff that we know. Well, if we look at our problem here again, where do we start? Vertically, where do we start? Well, we start on the ground right here, right? So right here, y is equal to 0. Well, if we look at where we end, we also end on the ground, and so y over here is also equal to 0. And so what that means for our equation is that where we end up at the end of this trip is 0 on the ground again. And where we started was on the ground, okay? And so when we start plugging in our numbers here, we know that that those two are already zeros. Those are going to be zeros. All right, so let's plug in the other stuff here. Vy was 17.3 meters per second. And the time, we don't know the time just yet. And 1/2, we know that g, if we're on Earth here, is negative 9.81 meters per second squared. And again, t, we don't know yet. Now, John Lopez is going to get really excited here because this is going to look like it's going to be a quadratic equation. And frankly, you could do it as a quadratic equation. It's already set up so that you're equal to 0 here. But what we're going to find out is because this term right here is also 0, it turns out we can actually factor out a t here. So let me clean this up a little bit. And essentially, we're going to kind of, well, let me just rewrite it here. 0 is equal to, I'm just going to get rid of this second 0 here. So this is 17.3 t. I'm going to drop the units here for a second. And when we multiply this through here, we've got negative 4.905 t squared. Okay. Again, if I factor out the t here, in other words, since I've got a t here and a t here and no other terms except for the 0 over here, I can actually factor that out. So I'm going to rewrite this here as 17.3 plus negative 4.905t. Right? I just factored out this t. Well, that means that in order for this to be 0, when I multiply t times this expression right here, that means one of those two has to be equal to 0. Well, we know that time is not equal to 0, right? We know that time is not 0, not equal to 0. So basically, I'm just going to kind of eliminate this t here. It seems like a little bit of cheating, but if you think about it logically, it makes sense that we know that this takes more than 0 seconds, right? So what that means is that 17, I'm going to rewrite this again here, 17.3 plus negative 4.905t is equal to 0. Or if I rewrite it again, I can make that 4.905t is equal to 17.3. I just sort of take one to the other side. So that means t is equal to 17.3 divided by 4.905. Well, let's stop and think a little bit about where this came from. What was the 17.3? Well, the 17.3, that was, if I go all the way back up here, that was my initial vertical velocity, right? Based on the angle and the initial velocity. So I could sort of rewrite this generically to say that the time is equal to the vertical velocity, the initial vertical velocity, divided by, where did this 4.905 come from? Well, if I look up here, 4.905 came from 1/2 times g. So in other words, that's always going to be the same, right? As long as we're on Earth, as long as gravity is always going to be 9.81 meters per second squared, or negative 9.81 meters per second squared. 1/2 of that is going to be 4.905. So that time factor is always going to come down to this. It's going to be, I'll tell you where that comes from. Where that comes from is you have your initial vertical velocity here that we started with. Well, when it gets to the top of the apex right here, the vertical velocity right here is equal to 0. Okay? And then when it gets back down here, comes back down to the bottom, that initial vertical velocity is regained. So, in other words, it starts at Vy over on this side, and it goes to 0 up here, and then it goes back to Vy over here. So in other words, it takes half that time to lose it. Well, why does it lose it? Because of gravity. That's why we use the 9.81. And then it takes half that time to regain that speed. So that's why basically it's the initial velocity divided by half of gravity, because it loses it and then regains it. So it takes twice as much time. All right, so for our problem, that means, let me plug this in here, 17.3 divided by 4.905, that means t is equal to 3.53 seconds. Okay, now remember what I said earlier was that t is good for both of these equations. We found it using this equation, but it also works for this equation right here. And that's what we're going to do right now. So I'm going to change color here just to show that, show that we're doing the horizontal here. Now the x is equal to the, whatever x position we're at is equal to wherever we started, x initial, plus vx times t. Well, sort of like we said with the vertical, the horizontal starting position is just 0, right? Unless we're told otherwise, we just kind of assume that is 0. The horizontal velocity, if we scroll back up here, we found that the horizontal velocity was, where was it? Here it is. There we go. Vx is 10 meters per second. So we've got 10.0 meters per second. And the time we just figured out was 3.53 seconds. 3.53 seconds. So this is very easy and tells us that the x, or the range, is 35.3 meters. So you can use those equations to figure out the range in this case, or if we had, other parts of this, right? In other words, if we had we could find the initial velocity or the initial vertical velocity, the initial horizontal velocity, and find v using this relationship right here, right? If we have vx and vy, we can find v. Or we can find the angle. If we have vx and vy, we can use a little trigonometry here. I guess I can add one more thing to our little list here, and that is, let me get a different color here. Let's see, theta, right, the angle is equal to the arc tangent, right, of vy over vx. Right, does that make sense? Right, this angle right here is the angle whose tangent is opposite over adjacent, right? Vy over vx.